So this video is going to look at section 2.4, looking at part 1, a little bit about the real zeros of a polynomial function. We want to look at a couple different things, particularly kind of summarizing the things that we learned when we looked at our activity from section 2.3. So some things we talked about when we looked at our chart when we did them in section 2.3. We know that when we're looking at local extremas, that's talking about mins and maxes. So if we wanted to figure out how many local extremas we have, we know that one of the things we were able to calculate from our table was if we were to take the number of mins and max and add 1 to it, we got the degree of the polynomial. So we would say that a polynomial function of degree n has at most a combined n minus 1 local extremes. So if I add the maxes, local maxes, plus mins plus 1, we should get the degree of the polynomial. We also noticed that if I was looking in terms of the zeros, that whatever the value of the degree was going to have the same number of zeros. So if we're talking about degree n, we would know that it has at most n zeros. Now we know it doesn't necessarily have n real zeros, some of them could be multiplicity as well, but the maximum number of zeros that we could have would be the same number as our degree. We also looked at something with our n behavior, and we said that it depends on 1, if the even degree or odd degree of your highest degree, and also the leading coefficient, whether it was positive or negative. So we know that basically they had this general shape. When we had something that was an even degree, a highest degree that was even, and a positive leading coefficient, we know the n behavior in terms of limits. As x approached both infinity and negative infinity, it went to positive infinity. Now what happened in between, we don't necessarily know unless we look closer at the graph, but we know the n behavior is going to have this pattern. And then of course if we have a negative leading coefficient, we know that's going to flip over the x-axis, so it's going to end up with n behavior that's at negative infinity. We also know that if our degree is going to be an odd degree, then they're going to have n behaviors that are opposites. And depending on whether the leading coefficient was positive or negative would decide which way is going to go which way. So we know that if it has a positive leading coefficient and the highest degree is odd, we know that when we go towards positive infinity, our y values are going to go to infinity, and when it goes to negative infinity, it's going to go to negative infinity. And we know when we have a negative leading coefficient that it's going to flip over the x-axis, so the n behaviors are going to switch. Again, we don't really necessarily know what happens on the inside, so I'm just kind of just drawing a little graph to kind of show that, but we do know that that's going to be kind of what the basic shape looks like. We also know that if I have something in factored form, we can easily tell the multiplicity. So when I'm looking at this problem, I know just by looking in the fact that a factored form it is, that we actually have 2 unique zeros. The first zeros that I have are going to be when x equals 3, and I know that has a multiplicity of 2 because my exponent here tells me that. I also know that I'm going to have a 0 at negative 5, and that's going to have a multiplicity of 4. We know that because of our exponent up here. We also know that if I take my exponent here and here, my 2 multiplicities, and I add them together, this will tell me the degree of this polynomial. So we know that this polynomial is going to have a degree of 6. So if I wanted to kind of sketch out what I know about this graph, I know that if it has a positive leading coefficient with an even degree, we know the n behavior is going to end up looking like something like this. We also know that we have 2 zeros that we can see on the graph, and because they have multiplicity, we know that that's going to happen is that those 2 values, because they are even, they're going to kind of go back in the same direction that they came from. So if we were doing a quick sketch to kind of look at what this would be, so we've got a value somewhere over here at negative 5, and a value somewhere over here at 3. We know that it's going to keep going in this direction. We know it's going to keep going in this direction. We know that at those zeros that it's going to go back in the same direction it came from. And what happens in between here, we're not really sure of because we don't really know that much without actually plugging in points. But if I asked you to sketch a graph of what this looks like, this would be minimally what you should be able to give me. I mean, we can know that it's not going to cross through the x-axis because of the fact of the zeros that we have, but we don't know exactly what happens in here. So this would be a quick sketch of what we know just based on this simple problem. Remember that we also talked about that even on multiplicity, and so remember that if it has an even multiplicity, we know that what's going to happen at the graph is it's going to go back in the direction it came from. So in this case, I have a 0 at x equals 1. Because it has a multiplicity of 2, we know that of course what's going to happen is it's going to go back in the direction that it came from. When we have the value, when we have an odd multiplicity, like at x equals negative 2, with the multiplicity of 3, because it's an odd multiplicity, we know it's going to cross through the x-axis at that point. Again, looking at our exponents here, 2 plus 3 is going to give us 5, so we know that, assuming that these are all the real zeros, that we're going to have something in degree 5. We know that the leading coefficient is positive because we're assuming it's positive 1. So we know that the basic end behavior of our graph is going to look like this. So if I wanted to sketch a quick graph of what I know I'm going to have some value over here at -2, some value over here at 1. We know that because the end behavior is going to go in this direction. We're going to draw something that looks like this. I'm going to draw something that looks like this. And I know that at the value of 1, we have multiplicity 2, which means that instead of crossing through the x-axis, it's going to go back up from that direction. And then I know at -2, because it has an odd multiplicity, it's going to cross through. So what happens here, I'm not really sure. There's probably some moving around that's doing, but just from this function that we have right here, we should be able to draw this quick sketch of a graph. Okay? So remember, if the multiplicity is even, the graph doesn't change the sign, or it goes back in the direction it came from. But if it's an odd multiplicity, it's going to cross through the x-axis. Something that seems a little confusing, but it actually is pretty straightforward, is something called the intermediate value theorem. It's just a fancy name for basically saying if you're trying to find where a 0 is, take a couple values. So if this is my function right here, and I wanted to figure out kind of where the zeros are, 1, I know it's going to be to the 9th degree, so there's going to be at most 9 real zeros. But it's not something factorable. Without a graphing calculator, I really wouldn't even necessarily know where a 0 is going to be. But we can do what's called the intermediate value theorem, which says let's pick a couple values. Now, I just chose -5 and 5. You could choose two totally different values. They don't both have to be the same number, one positive, one negative. One does not have to be negative, one does not have to be positive. But what the intermediate value theorem says is if I look at the value that I would get, so for example, if I was to plug in -5 into this equation, and also into this equation, plug in 5. What would be the sign that I get? So I don't really care about the actual value, just what would the sign be? I know that if I plug in -5, this is going to be a really big negative number. This is going to be a positive, but +5 plus 50 is not going to be enough to get rid of this negative value here. So I know I could figure out exactly what that value is, but really all I care about is I know this number is going to be a negative number. I also know that when I plug in +5, 5 to the 9th is going to be some really big positive number. Even if I subtract 5 by adding 50, these are really insignificant here. 5 to the 9th is a pretty big value. So I know that when I add up all these terms, it's going to give me a value that's positive. All right, so here's what's most important. This is what the intermediate value theorem says. If you plug in a value and another value, and you find that they change signs, so it doesn't have to go from negative to positive, it can go from positive to negative. But basically, if these two values have different signs, this tells me that somewhere in between these two is going to be a 0. Because what had to happen is probably it had to change from positive to negative, and if it's going to change from positive to negative, it's crossing through the x-axis. So it's a quick way to find out approximately maybe where a 0 might be. And again, I chose two values randomly. You could choose any other values. But if the signs are the same, that means there's probably, depending on how large a range that you picked, there's either going to not be a 0 in there, or you already passed it maybe, and it went back in the same direction it was coming from. So maybe there's multiple zeros in there. So that's basically what the intermediate value theorem says. We don't use it a lot, but it's just kind of a way to kind of quickly determine where a 0 might possibly be. This tells me there's definitely going to be a 0 in there. We also have something called the remainder theorem. This is actually really helpful and saves a lot of work if you remember how to do it. If you divide a polynomial function, f of x, by some factor, x minus a, then the remainder is always going to be what f of a is. So what does this mean? If I asked you to divide x cubed plus x squared minus 10x plus 8 by the factor x plus 4, and all I cared about was finding the remainder, I don't have to do all the work to figure that out. Yes, this is easy to do synthetic division, but I don't have to do this. What the remainder theorem says, if the factor is x plus 4, then I just need to find out what is f of -4, because that's the 0 that would go with this factor. If I can figure out what f of -4 is, then I have the remainder. So all I need to do is plug this in, and then plug that into my calculator and find out what the value is going to be. If I plug this into my calculator, I get a value, in this case, of 0. So this tells me that the remainder, when I divide this out, is going to be 0. It's not always going to be 0, but whatever the remainder would be is going to be there. So it's a quick way to find the remainder without having to go through long division or synthetic division. So remember that if all you really care about is finding the remainder. It's called the remainder theorem. So how does knowing the remainder really help you? Well, there's this thing called the factor theorem, and it basically says that a polynomial function f of x has a factor x minus a if f of a equals 0. So if we think about our last problem, before we got a value of a remainder of 0, that means that x plus 4 was a factor of that polynomial function. Here's another one. So let's say our function is p of x equals 3x squared plus 7x minus 20, and we want to quickly determine if x plus 4 is a factor. Well, that means that we need to look at the 0 of negative 4. So we're kind of using our combiner of the remainder theorem with the factor theorem. So the remainder theorem says plug in negative 4. What do you get for the remainder? So we plug in negative 4, and we see what we get. If the value that I get when I plug it in is 0, which in this case is what you get, then this tells me yes, because the remainder is 0, this is going to be a factor. So that's the factor theorem. So the factor theorem and the remainder theorem kind of go hand in hand. And I'm not going to ask you to remember what's the factor theorem, what's the remainder theorem. Just know how to use them. If I ask you to find the remainder and I give you a really big long function, you don't need to use long division or synthetic division to solve it. And if you also want to quickly determine if it's a 0, all you need to do is see, is the remainder going to be 0?